Welcome to the class of Digital Signal Processing. In this video, we are going to see how to design a digital filter using Matlab. What we want to do is we want to build a digital filter. Filtering is in the time domain, is a convolution. We know that is equivalent as a spectrum. People call that a spectrum analyzer, which we are dealing that easily in spectrum because it's a multiplication. For digital filter, we have those finite impulse response filter, infinite impulse response filter. So digital filter is something represented with Hn. So it can either be finite impulse response or infinite impulse response. The difference between these two, well, finite impulse response, meaning that Hn is I have a finite support. So I have some values H0, H1, all the way to Hm. If I have m plus 1 non-zero element, this is causal, so it's starting from H0. Versus infinite impulse response, if it's causal, that I'm starting with H0, that's a non-zero value, H1, but I will have infinite many of those parameters. So how do we actually implement? Well, implement FIR, that's simple, you're doing convolution. Now, how do we really implement IIR system if you have infinite many of those non-zero edges? Well, we are implementing that by feedback loop. Remember that we're not just writing Yn equals to Hn convolved with Xn, but we also have in implementation, we have Yn is this part, we have something of Xn convolved with Hn, meaning that I'm taking the previous Xn minus 1, Xn minus 2 as well, and we write out here. It should not be Hn meaning the entire system, but just bear with me here, let's say H prime. But you still have this part, you still have some feedback. In that way, the overall parameters will be less. The parameters here is maybe alpha 1. This is, let me just call it alpha. Beta sub n. This alpha 1, you have alpha 2, Yn minus 2. And in that way, the overall numbers of parameters will be small. It will even be smaller than FIR filter for certain cases. You won't have the same performance. To design a filter, we're starting from specifications. So we want to have Hn that given some specifications. And then you need to generate a filter. What are the specifications? Specifications is the requirement that we want. Usually that means the low pass filtering, high pass filtering, band pass filtering, band stop filtering, and then you need to give the stop band. What is the pass band width? Or the cutoff frequency, if you're doing low pass, high pass, what's the cutoff frequency? Those are the specifications. And in making this filter Hn, it's desirable to have this, as we want to have a linear phase response. Linear phase response in the passband, at least in the passband, in the bandwidth that I want, FIR system versus IIR system. Which one do you think that will have linear phase? In fact, FIR system will provide a linear phase. IIR system, very difficult to say. Most likely it will give me a nonlinear phase output, nonlinear phase filter. Linear phase is that if I'm looking at the phase term, the angle of H omega, this is in frequency, it's linear. It may or may not go through the origin. But in the frequency, it's linear. So if I'm taking the band of interest, this is my passband, from W1 to W2. In this range, it is linear phase. Versus IIR system, that's just taking band of interest. This is my passband, W1 to W2. It can be any shape. It's non-linear. The reason for this to be linear is because it's FIR filter. What we do is we are really taking the input and we have delayed input, adding all these together as my output. What I meant is what we do is we have xn plus beta 1 times xn minus 1 plus beta 2 xn minus 2. So that's all we have, right? This is FIR filter. All we do is we delay the input and you putting them all together give me yn. I don't have anything feedback. So that is a delay. Delay just is caused by the linear phase filtering. So the entire thing, the entire HN is linear phase. In contrast, for an IIR system, because I have yn, you have all these xn plus. You also have this term. You have feedback term. It's actually coming from the left of the equation and move to the right. So you have this part. And the entire thing from x to y is h. Because of that, feedback will cause a nonlinear thing. With the specifications, we want to find a filter according to a design requirement. We work directly in the frequency domain. Let's look at only the amplitude of these. So that's my absolute value of h omega. We know if you design that FIR filter, that's a linear phase. If it's IIR filter, it's most likely it's a nonlinear phase. But let's throw away the phase issues at first. We just look at amplitude. I want to make sure that amplitude according to our specifications. Look at a simple one is a low-pass filter. So low-pass filter, I have a cutoff frequency, omega c here. What I want to have an ideal case is like this. Oops, what have we done? Cutoff frequency, and then it's 0. So I want to have a 1 here, 0 here. Low-pass filter, right? From 0 to omega, we have passed the signal. From omega c, cutoff frequency, to pi, that's the highest frequency, I want to have all zeros. That's a low-pass filter. We're looking at the amplitude of my frequency response, h omega. In practice, we're not going to have that. The reason is that if you have this in the frequency domain, in time domain, it's a sinc function. So you're not going to have a finite impulse response anyways. You're going to have a hn. It's not even causal. The hn for this guy, it looks like this. It's a sinc function. It goes forever. In time domain, it goes forever. We have to truncate it somehow. So if you truncate it, as we mentioned last time, you truncate this, you are going to multiply a rectangular function in time domain. That means I'm going to convolve the sinc function of this frequency ideal box. So it ends up something like this. It's going down here. And of course, if I'm looking at the amplitude, if I'm looking at the amplitude, absolute value, there is no negative part. So it should be all positive. Looks like this, all positive. So that end up with. So what does that mean? Well, we are going to have certain values that's not perfect. We have a ripple here. We have another ripple here. This ripple, let's say, is between the range of 1 plus delta 1 to 1 subtract delta 1. That's our design specifications. I want to say, well, in the passband, I want to have a passband ripples in the range of delta 1. This is a ripple. We call that, this is delta 2. In the stopband, I'm not going to have ideal zeros, but I'll have a ripple. The ripple is in the range from 0 to delta 2. I will have something here. This is a transition band. We're not going to drop so sharply, ideally from 1 to 0. We're going to drop down over a band. This band is coming from here to here. We call this W sub P, stands for the passband frequency. This is W sub S, stands for the stop band. So we have this transition band in the middle. And I call this part from here 0 to omega P. This is my passband. Passband for the low pass filter. From here to here, this is my stop band. Stop band for the low pass filter. And then whatever is here in the middle, that's my transition band. Transition band. What I can do is I can define those two frequencies, WP and WS, give you the passband frequency, stop band frequency. So in that way, I define the role of the transition in the middle. For the passband ripple, we'll define a passband ripple called A subpass. Putting some numbers to it. That is -20 log base 10. 1 subtract delta 1 plus delta 1. So we know if you are using that, that's a ratio in dB. We have this this lower line divided by the upper line, and then put a negative sign here. So actually, we are trying to make this positive sign. So this is in dB, and that defines the passband ripple. And then I have another value called stop band ripple. A sub stop, that is equal to -20 log base 10 delta 2 over 1 plus delta 1. This is also greater than 0. We are using 1 plus delta 1 as my benchmark. That's the highest value I have in this filter absolute value of H. So delta 2 is the value here. Compare with the highest level. And we put a negative sign here, make sure that this is also a stop band. Value is positive in dB. So what we do is we have some numbers as our specifications for filter design. And those are the numbers which is a passband ripple in dB, stop band ripple in dB. I have a passband frequency, omega sub P, stop band frequency, omega sub S. For a low pass filter, of course, I need to know that's a low pass filter. For the high pass filter, similarly, you go the other way around. You understand the passband, stop band. We exchange the values. Stop band actually is smaller. What about a band pass filter? Band pass filter is something like this. Ideally, it looks like this. Well, we just need to define more of those. So in practice, I have ripple here, transition here. I also have a ripple down here. Transition here and ripple here. So I will have another set of passband stop band frequencies, another set of stop ripples here, stop ripples. So you define that, and that will give me the specifications of a passband filter. And you can similarly have a stop band filter with all these specifications. All right. Let's see how we can use in Matlab to deal with these. In Matlab, we can use a command for the filter design. Filter design, I believe that's the command for that, for the filter design in the latest version. It changes all the time. Typing the filter design, it pops up this window. This window gives me very nice pictures for the filter specifications. So if you look at this, we have all these filter specifications. Filter specifications we are dealing with, in this case, I'm dealing with a low-pass filter. You can change it here. I'm doing a low-pass filter or high-pass filter. If I click high-pass filter, that's going the other way. I need to have this as my passband, this is my stop band. So we're dealing with a low-pass filter. And that I have passband frequency f sub pass, stop band frequency f sub stop here. Passband ripple is here. This is passband ripple in dB. That is actually this lowest level over the highest level in this, and we are using the dB range. Here, this is the stop band ripple. So that's the stop band ripple divided by the highest peak that I have. There are different ways we define that. In Matlab, some of the Matlab code, instead of using the highest 1 plus delta 1, it used the middle sign here. It used the median sign here. So that is 0 dB in this case. Instead of doing this, sometimes in some of code, Matlab, you can change that to divide by 1. So it's just the log of delta 2. So you compare not with the peak, but you compare with this line here. But that's just how you define it, or it's very simple. Now, what I want to do is I want to define what I have for these real numbers. And let's say I have this is my pi. So that is the highest frequency that I have. And it writes here f sub s over 2. F sub s, what is that? That's the sampling frequency. Well, pi is the Nyquist rate, which is the sampling frequency divided by 2. And as we know, sampling frequency has to be twice as high as the highest frequency in the signal. So indeed, this stands for pi if you look into the radians. But if you give the unit in hertz, that is fs over 2. That's the sampling frequency over 2. So what we can do is I need to put some values. In this, by default, I have the sampling frequency is 48 kilohertz. Put it here. And the passband, as here, is 9600 hertz. Stop band is 12 kilohertz. So let's see, putting all this. So it's defined somewhere there. And then this is 24 kilohertz. In the high, that's the highest I can have. Then I want to design a low-pass filter using finite impulse response to implement that. Everything is here. Unit is dB. The passband ripple is here. The ripple is 1 dB. Stopband ripple is 80 dB. That means it really wants to attenuate everything here. It's not attenuate all the way to 0, non-ideal, but it's quite large drop. It's actually drop 80 dB. It's a dB as a unit, right? So it's really a very large drop. Let's see what we have. Filter design. That's what we have. So it gives me a filter. It's showing here. It's showing me the frequency response of H. Actually, that's absolute value of H. So we have this is magnitude in dB. So we have some ripple here instead of a 1. In dB is instead of a 0 dB, we get a ripple here. This ripple is in the range of 1 dB. Then we have a drop across my transition band. Here is the stop band ripple. Stop band ripple that we see here. Actually, this is the delta 2. Delta 2 is 80 dB down. Actually, this is compared with the highest one. So it's 80 dB down. That's a ripple of the stop band. Now, how many coefficients that I have? It's order of 50. I actually have 50 coefficients. So Hn non-zero values are 50 of non-zero values. And let's look at some other pictures for that. So here I have seen the frequency response of that. This button is for the phase response. Click that. Phase response is linear. It's linear. Here it goes down in radians linear. If you see here, it's a little bit because in the stop band, it is actually linear. FIR is linear, but you just wrap over pi, wrap over 2 pi. It will continue with one linear line. We can also look at this is group delay response. Group delay is the phase, the theta, the omega, and put a negative sign here. And that, indeed, the group delay is a constant. So we have a linear phase because we increment with FIR. We also can have a magnitude and a phase response. We're putting that onto the same part. So here, the blue curve is the magnitude response. The red line is the phase response. Here's the phase delay. Phase delay here is constant 0. We can see the impulse response. Here it might have impulse response, this button. So what is the impulse response? Well, that's a sine wave, right? But it's a truncated sine wave. So, excuse me, the sinc function, sinc wave. It's a sinc function, but that is a truncated sinc function. We have within this window, we got some non-zero values, but we can still see it's a sinc function. You can also see this picture, very nice, the post-zero picture. We have 50 zeros. We have 50 zeros. This is a unit circle. We have 50 zeros. That gives me a low-pass filter. If you go to the higher one, it's really close to 0. This is the low-pass filter. Where are the poles? Where are the poles for this filter? The poles are deformed onto the origin. We got 50 poles here on the origin. Well, theoretically speaking, I have the same amount of poles and zeros. So you have 50 zeros, I have 50 poles. But those deformed poles in 0, it really doesn't show on my filter of H omega. The reason is that I don't have denominator. So for this case, where are the poles? Because you just said you're using an FIR filter. I'm using an FIR filter. FIR filter H omega, we have only B omega. We don't have over A omega. This is a polynomial in the denominator. But in FIR filter, this guy goes to 1. I don't have poles. I only have 50 zeros here. So you spread this out. This becomes a multiplication of omega. If it's in the Z domain, I have a C. I subtract the like this polynomial. So I from 1 to 50. And you, of course, you got a constant, you have a parameter here. So those are the zeros. And you replace that Z with e to the power j omega in frequency. But we don't have any poles. And they are deformed onto the origin. We don't have denominator. That in terms of time domain, this is x, y over x equals to b omega over a omega. And we know we don't have a omega, so we have only b here. So that gives me equals to b times x. Indeed, because my output only determined by a convolution of my, in this case, b, involved with xn. Right? This is actually my h here. So this is my h here. That is a finite impulse response function. I convolved with a finite amount of those non-zero HNs. I don't have a feedback. I do not have multiply this. I don't have this term. This term is 0. So we have no 0 in this case. All this no poles in this case. All the poles are deformed onto the origin. That makes sense here. Well, that's a lot of orders. That's a lot of parameters, 50 parameters for a very simple filter. Can I reduce that? Can I reduce the numbers of those parameters? Well, then you need to use an IR filter. As we said, IR filter, you have something that is, we got a feedback. But in a sense, I can reduce the number of overall parameters. Let's see, I'm going to use an IR filter, doing the same thing, or the same specifications for frequency, specifications for the magnitude of passband and stopband. Design filter. Now that's what we have. Okay, we directly look into, this is the zero pole. So I have 31 zeros and 31 poles. In this case, I do have poles. I got a feedback. I have the denominator term. These are the poles around here. And the zeros, in this case, zeros are actually all the way to pi. Right? That's highest frequency. If you look at the magnitude response picture, it looks like that. Well, I have, actually, this is dB's case. So you still have the transition band from 9600 to 12000 here, transition band. This is a pass band of ripple 1, and this is the stop band of ripple. Stop band is 80 dB down. If you look at this is dB sense, so 0 to 80 dB is already here. So it's going down pretty fast. For the amplitude response, look at the phase response here. It's non-linear. It's not a straight line. It's non-linear. Well, we expect that. We are using an IR filters. We're putting these together. We got in the pass band. It's okay. It looks like a linear line, but it's a little bit curved here. Group delay. Group delay is not a constant. Group delay, we do have a varying number here. That's the impulse response. Impulse response in this case it's actually going on forever. It's going on forever. It's causal, so it's starting from 0. It's going on forever. For this is, we have seen that. We have seen the 0 pole. We only have 30 order of 31. The coefficient, the order has been reduced. Can I do even better? Well, you can do different IR filters. We can try another. For example, let me try this Chebyshev type 1. Chebyshev type 1, what does that mean? Well, remember we truncated in the time domain, right? Using a rectangular box. So if you, instead of using the rectangular to truncate in the time, I'm going to use a window, as we will see later time. I'm using a window of Chebyshev window, or using a butterfly window of any window. Then I can smooth the truncation in time, so I can affect some of the response in the frequency. Let's see, I'm using all the other specifications are the same. And I have the IR filter. What I want to do here is I match exactly in the passband. Stop it. I want to match in the passband. Design the filter. Okay, so here, passband is pretty good. It really follows. That's within 1 dB. The order is only 13. Reduce the number again. Look at the amplitude and the phase. So here is my amplitude response. Low pass filter. Phase is nonlinear, as we expected. So the group delay is not constant. It's kind of this weird varying number. What about 0 pole? So here is the 0 pole plot. I have 13 zeros at pi at -1 in this complex plane. And I have 13 poles here, around here. And then make sure that I will amplify my low frequency part and give me the effect. That's very nice. Now let's see how we can make use of this filter. Now we design a filter in Matlab, how we can import this filter that we designed, and then to work with our signal. Let me give an example of FI. This is my FI filter, this design. What we need to do is we need to export you can export the filter itself, HN, into the Matlab environment I'm working on. You can also export it to simulate a model. You can generate a Matlab code so that generate that filter. You can embed the Matlab code into your Matlab script. Export filter design. Export as a object. Let's call it HD. Looking to my workspace here. Now I have a workspace. I got an object called HD in Matlab. What we're going to use that is using the filter command in Matlab. You can look at this help. But basically, it is a filtering. If you have this object, it's very easy to filter the object with a signal. Let's say I get a signal. That's a test signal. N from 0. Time from 0. Make it simple. Test signal. Test signal is a random noise. How about that? It's a random noise of dimension 100,001. Let's plot this test signal. So here's what we have. The test signal here is we have. This is noise. This is noise. Now I can also plot this showing in the frequency domain. So what I do is the ft on test signal, and of course I want to see the absolute value. I only want to see the magnitude of that. It's here because I have a white noise, so it's everything. It's from 0 to Matlab. Remember that's 0 to 2 pi, right? This is the sampling frequency. So everything that's it's almost a constant across all the spectrum. Then what we need to do is I need to filter the signal using the filter I just designed, HD. Let's call this the filtered signal equals to filter HD, the test signal. I missed a spelling. Never mind. Let me just use that. Okay, that's it. I just used my filter, but I designed a low-pass filter to work on the test signal. It's a random noise, and then I got the output is called the filtered signal. Let's plot in the time domain. Plot the filter. It's probably not seeing anything because it's still noise. It's just low pass. It's still noise. But let's see if I can show this in the frequency domain. Plot T of filtered. It looks like this. It looks like this. Now what do we have? Well, we got a filtered signal. It's starting from in the middle because in Matlab we know this is pi. This is pi. In Matlab this is 0. DC. This is pi. This is 2 pi. Sampling frequency. So we actually only just look at from 0 to pi. This is a mirror. We see that indeed it's a low-pass filter. The lowest signals has been preserved to the output. The signal components that beyond 112 kilohertz will be filtered out. Because my filter is 80 dB down, so it's pretty good. It's almost notify everything here on the high frequency here. So we indeed go through a low pass filter. So you can use that very easily working with your own signals in project. You can filter out, in this case, I'm trying to filter out the high frequency components, and maybe there's a high frequency noise. And you can do a high pass filter to filter out low frequency component that can be low frequency noise. You can filter it out. Okay. And then now, lastly, what I want to show you is that if I do this, if I have this filter, I want to export that. Remember that I can export that to Simulink model. That. Sometimes using the Simulink, it can help us to design a digital system very easily. Okay. So now we have the model is implemented as a Simulink model, and I want to realize this model. So click Realize Model. Matlab, including Simulink, are very nice tools. Can ease our work for design a filter. We understand the theory behind that, but we don't need to write everything from scratch. Usually for some modern tasks, we always use some tools. We use tools. In this case, we are using programming tools. Working with practical problems is very easy. We understand the specifications of the filter, how we design the filter starting from the ideal case, and then we define some non-ideal limits, the ripple, the band, the transition band. We design all these nonlinear limits, and then using that to design, to generate a filter that can work in Matlab. Okay, so now it comes out with the Simulink plot. So later on, if we have time, we'll see some Simulink. It's very easy. You can connect with input and output. So in the Simulink, we have a filter coming here. That's just a block, and you can connect this into the design that we have. And you probably after that, you give an output signal, and you can do an FFT and showing using a scope to see the signal. If you click on this, it will pop up the parameters for that. Pop up the parameters for this filter. Lastly, the other way around, if you build everything in Simulink, I can also do that to add a filter. What we have here is you click on the library browser. So if I'm already designed a system in Simulink, click library browser here. And I have a lot of Simulink add-ons. So we are looking to the DSP system toolbox. Within that, there is for the filtering, and the filter implementations. You click on that, filter implementations. I want to implement with a filter design. With a filter designer, you can implement all pass filter, all pole filter, for instance, all these things. I want to implement a filter design. So I move that onto my Simulink design. Design board. It looks here. So we have a filter design. And then I can click on that. Well, it pops up this window, which is our filter design window, and we are familiar with that. We know how to define the low pass, high pass, and using the specifications of frequency and magnitude. And with that, we can modify this filter from the Simulink and put that to be as a part of our system. Okay, that concludes what we need to discuss for today. And I've showed you how to use a computational tool, Matlab, to design a filter. It can really ease our work and using some tools. It's starting from the ideal case, what we want, we translate that into a specifications, and using that specifications to design those nonlinear limits. And using that to find HN, that's the digital filter. You can export that into your program import that into the Simulink and then link to the signal that you're dealing with.